Okay, welcome to the fifth video of linear integrated circuit. So in this we shall see the Astable Multivibrator continued version from the previous video. So we were discussing about the working of the Astable Multivibrator. So as the capacitor voltage is less than VTL, the output is VCC. Even when the capacitor voltage is above VTL but less than VTH, the output is still at high voltage. Once the capacitor voltage exceeds VTH, this transistor turns on. So this capacitor starts discharging through RB and the transistor, and that's why you can see the capacitor is discharging. So during that time, the output is 0. So this will be 0 till this capacitor voltage, which is keep on discharging, goes below VTL. So as the voltage of the capacitor goes below VTL, this will again set the flip-flop, which will make the output voltage as high here. So once the output voltage is high, the BJT is off, the capacitor again starts charging towards VCC through RB and RA. So this is the entire process what we looked in different stages, that is stage 1, stage 2, stage 3 and 4 and 5. So this is again the summary of the same Astable Multivibrator. In stage 1 we consider the capacitor voltage to be less than VTL. So in such case it will want to set the flip-flop. The output is VCC when the BJT is off, when capacitor is charging towards VCC through with a time constant of C into RA plus RB. Now you can see the flip-flop is set. So once the capacitor voltage goes in between VTL and VTH, the flip-flop goes to no change state, that is both R and S are becoming 0, 0. Output actually remains in the previous state of VCC. This was VCC, now you can see it is remained at VCC. So as long as output is VCC, the BJT is off, which will make the capacitor to keep charging towards VCC. So on its way towards VCC, whenever it crosses VTH, then it resets the flip-flop. So once it resets the flip-flop, output is becoming 0. As soon as the output becomes 0, BJT turns on. Now capacitor starts discharging. So when capacitor starts discharging, so as we saw in the previous waveform, now this is the position where the capacitor started discharging. So on its way towards 0, so wherever it goes, whenever your VC is greater than, okay, whenever the VC goes less than VTL, so then whenever the VC goes less than VTL, I can see this fourth stage corresponds to the capacitor voltage where it is less than VTH. This is actually the fourth stage of the capacitor voltage. Now capacitor voltage between VTH and VTL. So during that time, this remains to be there in 0 state. Output is in off state because the transistor is on. So as long as the transistor is on, the capacitors keep on discharging. As soon as the capacitor voltage goes below VTL, that again goes high. So likewise, so as the capacitor keep on charging and discharging, the output will be switching from VCC to 0 and 0 to VCC. When the capacitor voltage exceeds VTH, it goes to 0. Whenever it goes below VTL, it goes to high state. Now this is the design equation. So let us consider how to obtain the expression for the on time, which is the high TH. So we know the expression for the capacitor voltage VC is equal to V final minus V initial into e power minus T by RC. Substituting the initial voltage as VTL. So we are considering the expression for this VTH here. This is your TH, that is high time or the on time. So during this estimation of TH, you can see this is the initial voltage. So initial voltage of the capacitor is VTL. So VTL is nothing but 1/3 of VCC. If the capacitor is allowed to charge with infinite time, it will go to VCC. So V final is equal to VCC. But when time is equal to th, the capacitor voltage reaches VTH. So VTH is nothing but 2/3 of VCC. Substituting Vi as 1/3 VCC, Vf as VCC, and substituting T as Th, during that time the capacitor voltage is 2/3 VCC. Substituting all those parameters and substituting the value of R as Ra plus Rb, because we know that the capacitor is charging, it is through resistor Ra and Rb, so that's why we are replacing R by Ra plus Rb. So the equation comes out to be T on or Th is equal to ln of 2 Ra plus Rb into C, or which is nothing but 0.69 Ra plus Rb into C is the expression for the high time or the on time of the waveform. This is the resistors Ra and Rb through which the capacitor charges towards VCC. Now let us find out what is the expression for the off time, TL. Now we are looking for this TL now. So whenever we are trying to find the expression for TL, we need to know what is the initial voltage, what is the final voltage, and what is the voltage at T is equal to TL. So initial voltage is 2/3 VCC. Why it is 2/3 VCC? As you can see, whenever I want to estimate this TL, the corresponding input voltage or the initial voltage of the capacitor is VTH. So VTH is nothing but 2/3 of VCC. What is this Vf? Suppose if the capacitor is allowed to discharge for infinite time, it is now, we can see it is keep on discharging here. So this will keep on discharging like this. So ultimately it will go to 0. So that's why Vf is written as 0 volt. But at time is equal to T is equal to TL, the capacitor voltage has reached VTL, which is nothing but 1/3 of VCC. Substituting Vi as 2/3 of VCC and Vf as 0 and T as TL and Vc as 1/3 of VCC. Now you can see we are replacing this R by Rb. So Rb is the resistor through which the capacitor will discharge to ground. So that's why we are replacing R by Rb. That's what is, see here, this capacitor will discharge to ground through this resistor Rb, and this is the path, and it goes through the transistor and then finally it goes to ground. So there is a ground here, so this will be grounded. So the capacitor discharges to ground through Rb and the transistor. So as we discussed in the earlier video, the on resistance of this transistor is neglected compared to the value of Rb. Now rearranging all these terms, we get the expression for T off or TL as ln of 2 Rb into C, which is 0.69 Rb into C. So these are the two design equations for T on and T off, or TH or the TL. Now let us use this equation and try to design an Astable multivibrator. So this is type 1. In type 1, there are specifications given that Ra, Rb and C. We are asked to estimate what is the on time, off time and the duty cycle. In the first example, the specifications are Ra and Rb are 1 kilo ohms each, and the timing capacitor C is 0.1 microfarad. Using the equation T on is equal to 0.69 Ra plus Rb into C, we get the on time as 138 microsecond. Similarly, off time using this expression is 69 microsecond. So this is the timing of the output. Now corresponding, once we know the T on T off, we can certainly find out the total T and the frequency. So frequency comes out to be 4.83 kilohertz. And since we know the value of on and off time, we can find the duty cycle of the output, which is T on by total T, which is now 66.6%. So this is in percentage. Now similarly, we can estimate the value of on time, off time, frequency and the duty cycle for different values of Ra, Rb and C. So these are different examples. You can certainly verify these values, and you are also asked to estimate the on time, off time for these Ra, Rb and the C values. So you are supposed to find out what is T on, T off, the frequency and the duty cycle for these two specifications. So this is one type of design where the values of the components are given and you are asked to estimate the on time, off time, the frequency and the duty cycle. So this is evaluation using the T on T off. The other type of design, so will be specified the frequency and will be asked to design it for a given duty cycle, which is 0.8, 0.6, 0.7 for a different frequency. Now we are supposed to evaluate what is the on time, what is off time, what is the component values of RE and RB. So since we have only two equations and three unknowns, so we are assuming the value of C to be 0.1 microfarad. So let us consider the first specification where it is 1 kilohertz frequency and 80% duty cycle. So the value of C assumed is 0.1 microfarad. Corresponding to this 1 kilohertz and 80% duty cycle, the on time comes out to be 800 microsecond. Similarly, we can find what is off time. The value of on time and off time can be obtained using this equation, where on time is equal to total time multiplied by the duty cycle, and off time is nothing but total time minus the on time. So once we know what is on time, off time, we can certainly estimate the value of RB first. So because in estimating RB, we need to know what is off time, we need to know what is C. We can certainly easily estimate the value of RB. So we are first estimating the value of RB because we are knowing off time, we are assuming the C value. And since we know the value of RB, we can certainly find out the value of RA because we know everything except RA. So RA is coming out to be 8.7 kilo ohms. So similarly, you can note this frequency for this duty cycle, assuming a capacitance of 0.1 microfarad. Of course, the on time using this expression is 120 microsecond. The off time is 80 microsecond. The corresponding values of RA and RB are listed here. So similarly, we have done it for other frequency in the duty cycle. Because you are asked to perform the same evaluation of by assuming the value of C, find out on time, off time, the component values of the resistors. So this way you can comfortably design a Astable multivibrator for a given frequency and a duty cycle. I hope all of you understood the working of the Astable multivibrator using 555 timer and obtaining the expression for the on time, off time, and of course to design a Astable multivibrator given the component values, how to estimate on time, off time, and then the frequency resulting in the duty cycle. The other case, we have been given the frequency in duty cycle, so you can estimate the exact values of RA and RB to meet these specifications.